Okay, hello everybody and welcome. It's great to see you here at this Women in Engineering and Women in Power joint event to celebrate International Women in Engineering Day. So I'm just going to, my name's Annabelle Latham, I'm going to say a couple of words about Women in Engineering, which I chair, and then I'm going to hand over to Helena, who's going to talk about Women in Power. Okay. We are recording, just so that you know. Those of you who aren't familiar with the IEEE, just a quick word about us. We are the world's largest technical professional organisation for the advancement of technology, and we are dedicated to advancing technology for the benefit of humanity. It's full of volunteers, full of lots of different technical chapters, including electrical engineering, electronic engineering. Myself, I'm a computer scientist, and you can look us up. We're involved in lots of different things. I don't want to talk anymore due to time, so I'll just talk to you about the IEEE's Women in Engineering group. So we are quite a large group. We are in fact the largest international professional organisation who's dedicated to promoting women engineers and scientists. So our mission is overall to globally facilitate recruitment and retention of women in technical disciplines. But we are not, we're diverse. So we envision a vibrant community of women and men collectively using our talents for the benefit of humanity. A few little numbers. We've got over 20,000 members across the world in over 100 countries. And there are over 900 affinity groups, so affinity groups for countries, for student bodies, etc. In UK and Ireland then, which is the section that we're in, we are a very active group. We do lots of activities. I'll just give you a little flavour of what we do, but you can see on screen lots of different things we've been doing throughout the time when we could see people. It's been a bit different this year. And we were very happy to win the Region 8, which is Europe, Middle East, Africa, Women in Engineering Section Affinity Group of the Year Award, which is fantastic and recognises all of our hard work. Some recent activities that we have been involved in. So we launched a scheme called Women in Engineering Ambassadors. I'll tell you a little bit about in a moment. We've just launching some awards which are open to anybody, men, women across our region who don't need to be a member of IEEE. We're doing lots of events. So there was one the other week which had the IEEE president, who is a woman, talking, as well as some industry talkers. We do joint events with the technical chapters, for example, this event right now. We have a senior membership drive, so we're aiming to put on workshops to support women to apply for senior membership of IEEE, which requires a few references, so it's not a straightforward thing. We are generally pushing for gender diversified panels at all IEEE meetings, conferences, events, including our own. So we want a panel with a mixture on, and we're very happy to make a nuisance of ourselves contacting conferences to make sure they have a diverse set of speakers. We have a database of female keynote speakers so that we can support that. If you want to be on it, please let me know, or a member of the team. We are looking for people to add on. We do lots of outreach events. We used to focus quite a lot on schools outreach, science museum events, career talks, etc. when we were allowed to be out and about in schools. And we have a poster campaign. I'll show you a poster a bit later that we did for the Power and Engineering Society Women in Engineering event in a previous time. So Women in Engineering Ambassadors is a way of recognising a lot of our volunteers and their fantastic work. It's also an opportunity for us to mentor and coach people in terms of networking, career development, and also looking at projects relating to women in engineering, and to put on events. So there, Nagam is our lead for that program, and there's a couple of our first ambassadors. We launched it on the 8th of March this year, International Women's Day, and already we've done 3 events and we've got more coming, so it's fantastic. If you want to be involved, please get in touch again. That's a screen capture from one of our recent events with the IEEE president. And then a very quick note on our awards, because you might be interested in nominating somebody. So we have 4 awards which are looking for engineers across our region. Like I say, we will favour spreading across the different countries in our region, and we have an award for excellence in engineering, a technical award. We have a change catalyst for equal engineering. So for anybody, and like I say, it doesn't matter the gender, it just matters that they're in UK and Ireland. For driving change, that's a technical person rather than an equality diversity role. We have an award that we're naming after an inspirational engineer from our region. It's Kay McNulty Award this year, who's a software engineer was based in Ireland. Which is aiming to link really early career technical women, people with the Kay McNulty name and legacy. And then we have an inspirational volunteer award. So information will be posted out and will go on our websites at Women in Engineering. Please feel free to nominate. The criteria are that somebody must be an IEEE member. So whether that's the person nominating or the person nominated, or one of the referees, doesn't matter to us. We want it to be as widely available as possible. Here is one of our posters. Featuring some previous students in the Women in Power group. And we try and leave posters wherever we go to try and challenge the stereotypes of engineers. So if you want to be on one again, please get in touch. And then finally, you can contact us at our website on Facebook, Twitter, LinkedIn. Thank you very much. And I'm going to hand over to Helena now.
Thank you very much, Annabelle. Let me just share my screen as well. Welcome, everyone, on behalf of IEEE Power and Energy Society Women in Power. I hope you can see my screen, and I'll just start the slideshow. My name is Jelena Ponochko. I'm a lecturer at the University of Manchester and the chair of the Women in Power Committee in UK and Ireland. And on behalf of the committee, I can say I'm very happy that we have finally managed to organize this time an online event jointly with Women in Engineering. Women in Engineering is a wider group, I would say, at the IEEE level, and we are more focused on women working in power and energy domain. Before we continue, I'll just like to point out some housekeeping rules. So if you could please keep your microphones muted, and all the audio and presentations will be recorded, while the chat history will not be recorded. The recording of today's event will be available on a YouTube channel. I will let you know which one exactly. At this point, I do not know. A few words about Women in Power. We are a relatively new and small committee, but still we have been hardworking in the last few months. So we've organized several online events, unfortunately. Hopefully we'll have more physical events in the next few months. This is our committee, and you will see that some of the committee members will be presenting today in the technical part. Also, our Twitter, LinkedIn, profiles are available here. So if you would like to follow our events, you can follow these pages. You're also very welcome to become a Women in Power member. If you are interested in joining the committee, again, please get in touch. You can also get in touch using the social media. We have a lady who will be joining soon our committee, and actually she was presenting as a technical speaker in one of the previous events, and she really liked the whole idea of what Women in Power is doing, and she will be joining the committee. Now, what is it that we are doing? We are organizing events that should help our female, and not only female, any colleagues to develop their technical but also soft skills. We do not aim to make everyone a leader. Not everyone is born to be a leader, but what we want to achieve is to help people find the right career pathway for themselves. And so we are trying to liaise between people working in academia and those working in industry, but also to liaise between people who are at the start of their career and those who have already established themselves in their respective area. We are planning many more events in the future. So if you have any ideas what we could organize, or if you would like to participate in any way, please let us know, and we'll be very happy to see what we can do about it. Now, the program for today is given here, and before we continue, I would like to invite Professor William Heath, who is the head of the Department of Electrical and Electronic Engineering at the University of Manchester. The department has supported strongly this event, and I will just let Professor Heath say a few words before we continue. Thank you.
Thanks, Yelena. You didn't come here to listen to me, so I shall be as brief as I can. But I would like to welcome you to the University of Manchester. I'm really sorry it's a virtual welcome. It actually feels like things are getting back to normal, because as we speak, we've got the Lego League actually physically happening at Manchester, and there's also a robotics demo. So I hope at one of the future events we can invite you for real. But meanwhile, I'm very proud we're hosting this event. Diversity is really important for us. It's a high priority to make the department more welcoming for women, both in terms of professional staff and also in terms of undergraduates. But beyond that, all I want to say is welcome and thank you to Annabelle and Yelena for organising, and enjoy the afternoon.
Thank you very much, Professor Heath. I have stopped sharing my screen in order to announce our first speaker for today. Let me just try to minimize my screen and announce our first speaker for today is Professor Liangxiu Han, who has a PhD in computer science from Fudan University, Shanghai, China. She is currently a full professor of computer science at the Department of Computing and Mathematics, Manchester Metropolitan University. She is a co-director of Center for Advanced Computational Science and Deputy Director of Man-Made Crime and Wellbeing Big Data Center. Professor Han, the floor is yours.
Liangxiu, you're muted.
You're muted.
Sorry. Yeah. Okay. So good afternoon, everyone. Very nice to meet you here. And thanks very much for organizers to invite me, to having me here. It's really, being honored to be here. I think this is a very inspirational event. I'm hoping that you can enjoy my talk. I know that the power of data, but maybe in my talk, mainly, I think I'm going to talk about the data is not just the power, but all the old kind of data. Just a second, let me. Right. Okay. So my topic is meeting societal challenges, big data driven AI enabled approach. So I will start with what is a big data and our big data research and some use cases to tackle the societal challenges. So the big data, what is a big data? So for the moment, there are a lot of the instrument, a lot of for example, like gene expression data and also climate data, the square kilometer, the array data. So these are huge of data come from everywhere. So for example, the data collected by the SKE in a single day would take nearly 2 million of years to play back. And also, if you can see, here is the comparison between the 2020 and the 2021, the internet minute per minute, the data. So basically, so for example, compared to 2020, iPhone text minutes have risen from 19 million to 21 million. Online purchase have risen from 1.1 million to 1.6 million. And the WhatsApp messages per minute have risen from the 50 million to the 69 million. TikTok, so everyone's use it. So so big data, to me, I think it is really combination of the data analytics, machine learning, AI, and the technologies that collects and processes the data in an efficient way to assist in effective decision making. So maybe everyone already knows that the data currently, the people classify the data characteristic, big data characteristic from volume, velocity of and variety and complexity. So I think there are another two more V's, value and veracity. So here, sorry. Okay, so what is what we say the big data is actually, it's not something like we just say the volume. If the volume is big, we call the big data. So those the 5 characteristics they have to have. So the volume, by volume, what we mean is that the size and the scale of the data. And by velocity, that means the data in motion, means that the real-time captures data, analytics data, streaming data, especially I think the sensors data, time series data, stock market changing, and especially like your today's topic mainly is power, electricity. So it does capture the time series data signal. So it fits for this area. And the variety and complexity. So basically, we know that we have a variety of the formats. Sometimes it's text, sometimes it's the images and the videos. So structured data and unstructured data. And also 2 more ways, and the business value. So how this big data can generate like revenues in the business value, and also the quality and understandability of the data. So these are 5 V's that compose of as like a big data characteristic. So big data really can lead science discovery. So in terms of, because we have data, but in terms of technical challenges, because we were science and engineering. So technical challenges is that for us is try to make this large volume big data to make that become the low volume. And then to make this raw data, low value raw data become high value. And technically, so for us as a computing scientist or the computing or engineering scientist or engineering discipline, so what we want to understand with this big data, firstly, how to filter and reduce the amount of data, enable timely insight decision making. So this is concerned about how we build data analytics, computational modeling. And the second one is that how to process this large data efficiently. So because we can't just process the data in one single PC, okay? So we wanted to make our algorithm scalable. So how do we actually make our scalable? So this involves how we process the data, how we build the scalable system. So in this sense, to give you more concrete context, so maybe the parallel how we make our algorithm running in the HPC scale in a scalable way, so parallel and distributed computing, cloud computing. Cloud computing actually is another typically distributed computing. So here I'm just giving you some use cases and what we have done. So our big data research, so focus on this fundamental and applied research in big data. So we focus on the novel big data analytics, as what you just said, to address those challenges, what I just mentioned earlier in my previous slides. And then we try to build a scalable architecture that can facilitate such big data processing analysis. And we also, because we are not just develop fundamental approach, we wanted to apply this big data into the actual real life to solve the real problem. So that's application to different domains using various data sets. So our ultimate goal is to build a scalable big data driven production system to meet the societal challenges. That's the goal. So currently our research covers the healthcare, precision agriculture, energy, and manufacturing. So I think there is a little. So energy manufacturing. So the end of the aim is try to build the future sustainable society. So here are some selected projects what we have been working on. So for example, life science and healthcare. We have here the big data, the Royal Society funded project is a big data intelligence analysis, analyze large scale neuroimaging data. Our work is try to develop the fundamental approach in the machine learning, how to reduce large the data high dimensionality, and then how we develop efficient analysis for the analyze neuroimaging data to detect brain disease. And also the retina image. So we try to tackling the challenges to detect glaucoma disease. And also the gene expression patterns and the Horizon 2020, the image life. So this is life care science. Later on, I give you the specific use case. Right. Okay. So, and also we also have the project research have been working on the precision agriculture. So we try to developing the, for example, crop disease diagnosis, and also the nitrogen usage efficiency. So all these projects actually really tackle the real society challenge, but apply with the application of the big data technologies into it. So, and also smart cities, we also develop the machine learning algorithm to analyze the large data set to detect on the surface subject or object, and to detect the faults. So these all and also future cities demonstrate City World project. We try to build real-time big data analytic, energy data analytics form to analyze energy consumption data and to predict the energy consumption, to give the alert to help the facility manager to manage energy efficiency. So all these type data we have been currently working on. Some of the finished, but some of still ongoing. So we have the essence is we try to build the capacity and the capability to process and analyze different type of large data set. So build the capacity and the capability. And we build the data pipeline. We are not just as an academic, so we're not just doing the research. We really try to build the real product to really for the real use. So, so I give you the start with some use case. I think I'm conscious of time, and maybe I just give the brief, quickly go through this. So, scalable deep learning for Alzheimer's disease diagnosis. So currently, typical deep neural network require large amount of data to learn the parameters, so often reach to millions to obtain the higher accuracy. Training a deep learning models is both computational and data intensive. which way this may take days or weeks. So this is longer research and the production cycle. I believe some of you here, the attendees, already use this deep learning framework, and then you know the how long you take the how long the time you take the training the model. So our aims is try to build scalable deep learning framework. So from model perspective, we try to build reduce parameters, because how to reduce the parameters is important, and the size of the models. For example, model optimization, you want to quantitization, you want to pruning the model. And from a system architecture point of view, we want to develop parallel and distributed computing. So for example, we consider how we distribute. If you develop, although you develop a GPU, for example, you use one single GPU, you develop a deep learning model, that doesn't matter. That doesn't mean that it is scalable, you know. So you have to really consider, say, for example, how I'm going to decompose. If I want to make my deep learning model run efficiently on the HPC, how do I distribute my workloads or decompose my neural network layer into the different parts, and to running the efficiently on the multiple GPU or multiple computing nodes. Okay, how to map this task onto the various computing nodes. So how to the coordinate community subtasks to these computing nodes. So this is all the technical challenges we have to solve. So for this work, we focus on both these two aspects. Firstly, we develop efficient machine learning algorithm to detect Alzheimer's brain disease. So for example, we have already developed some 3D residue self-attention deep learning neural network, and that's been published, just been published, and also the multiple instance deep learning. And then after you develop this, is that enough? No, that's not enough, because whether it is scalable, you have to make this algorithm scalable. So that's why we also develop this what we call the parallelization approach to make this our algorithm scalable. So why we do this? So here is a brain disease. So if you can see, normal brain, as you can see here, and on my left hand side, and abnormal brain, you can see AD, on my left hand side underneath. You can see that there is a very obvious symptom, you can see. So that's why how we use machine learning to detect this, like how you can see the different the different parts of the impairment. And so yeah, so here is the some impairment and the normal cohort and the diseased part. So I'm not going to talk too much detail, but this is just the general brief, the work, proposed method. If you can see this proposed method, and later on we will use parallel and the distributed approach, and to try to make this this method to make it running on the efficiently. So here is a hybrid parallelization approach. I think if you are interested in the algorithm, so you can ask me to get the papers. I will send you paper, but for the moment, I think I'm conscious about time. I just talk about the concept, how we do this. And you can see here, this is some comparison result, and the accuracy, our algorithm accuracy is very high, is quite high, and also the visual deep learning model, we use the visual explanation of deep learning model, and the visual explanation, and the like this kind of like. You can see that my left hand side is raw images. Here, my right hand side is attention area that can show the interpretation. So this model is interprober model. So what we call it. So it can show help this the neuroscientist to interpret this, why this decision has been reached. So this result shows that our approach compared to the normal parallelization approach, as you can see, our training time is actually significantly reduced by, for example, the red bar is the normal data parallelization, and the blue bar is our proposed algorithm. So this already have some published papers. And then another use case is automatic glaucoma disease. I think it is still same. We developed the pioneer work for the glaucoma disease detection, use the big data, large data from fundus images from laser scanned images. And we have developed pioneering and developed the method. And here are some experimental results. Okay, so here are some quality output, and we have been finalisted as a UK ICT pioneer competition, very prestigious, and also have some industry follow-on support. So, and also these are the BBSRC funded project was we were looking at a gene expression pattern and all. So the project aims is try to label the big data. So if you can see, label the ontology term on my right hand side with the gene express patterns on my left hand side, on my right hand side in the images. So how this is a biologist's interest. They want to understand where is the humerus based on the gene express patterns. Okay, so I think this this process is how they acquire data. This data set is very big, it's 40 terabytes. So how we actually process high big data. And then we need to consider automated approach using machine learning, deep learning. And then we also need to understand how we parallelization, map reduce using scalable way, MPI. So these are some experimental results. Because what I'm saying, the HPC is high performance computing, but currently many people are doing the cloud. But the cloud is not mysterious, okay? It's just the distributed computing. But when you migrate your HPC, the like application to the cloud, you need to consider storage costs, computational cost, and the transfer cost. So this all has to be considered. So when you consider this data movement, because when you make your algorithm efficiently running, and then you have to consider the data movement. So in this case, we try to develop the fundamental research where we try to reduce the data movement, whether you want to move your data close to your program or whether you want to move your program too close to your data. So this is the decision making. So, but certainly the later is the most favorable. So we want to move our program close our data. We don't want to move the data. So here we have developed the data movement algorithm to reduce the to improve the computing efficiency. Patronet-based model to minimize running cost. So I'm not going to talk too much detail. We have the papers in terms of resource scheduling in the cloud and how we move the data. Okay, so this is the one is data in the healthcare. And we also have experienced a lot of data from the precision agriculture, for example, census data and image data as well, GIS data, historical data, forecast, climate, weather data, and also web social media data. All this kind of data we have built like a big data platform for crop disease diagnosis. We collect historic data, satellite image data, drone image data, camera data, and IoT sensors data. We build the big data platform, and we we develop deep learning models, scalable deep learning models for crop disease diagnosis. And then now we also having detect the nitrogen diagnosis. But here, just the use case for you. So similar principle applies. We also apply the same principles. We're looking at how we build the data analytics first, and then how we build the scalable data service platform. So, so first, the data analytics develop scalable deep learning models. So this is fundamental, develop a fundamental approach for the image quality enhancement and model interoperability. So here, I'm just giving the use case for the crop disease detection. So here we use the 3D data. It's very large data from drawn images. Okay, so we developed the deep learning models, and we have this video result. And here we also have to think in that how we actually develop the lightweight model, because here the GUI interface we showed to you is mobile interface. So you can see how we actually develop lightweight deep learning model so that it can embed into our mobile app. So this is all the mobile app. So we can do the live detection of the crop disease. So yeah, here I think how many minutes I have left? I think
you have a few more, three minutes more.
Okay, so here's some product demo. So I just give you a link. I'm not going to show here, but it's very, very nice. We already created some screencast. It's very professional. We created, currently this product are currently undergone the large field tests now in developing country. So what I just want to say is that we really wanted to create the real product. You know, here is here is the workflow. So basically, the farmers who didn't have the money to buy a drone, so he can request the third party to fly drone to their field, and then the third party drone operators will go to their field and to fly drone to detect whether there is a disease or not. And this disease, we have developed deep learning models that can detect the disease in real time, both in real time and cloud backend processing. So yeah, this is real time show to farmers, say, okay, your plot has disease or not. Okay, so yeah, I'm not going to show the video. And yeah, this is a video what we have produced for the mobile app detect the disease in real time. So yeah. Okay, so I think this application to smart city may be more fit for the today's talk is a smart cities project, what we have been working in the city web. So energy consumption. So our task is try to build the occupancy modeling and detection using sensors linked big data processing data analytics for energy saving in building. So in addition to that, I did have a PhD student. We're doing this topic to occupancy. So because we have this research, that's why we were involved to participate in the City Well project. So basically, the idea is that sensors inside of building, they deployed inside of building, and we use the sensors signals, and then we try to detect the occupancy behavior and patterns, and to inform the building management system, and say based on energy consumption. So for this research, we actually focus on firstly occupancy modeling, and we develop novel online dynamic hidden Markov model to fast and accurate process the analyzed online streaming data, we develop online multiple occupancy pattern detection. And then for the City Well project, we have the streaming all those kind of smart meters and energy devices. We have built the big data platform, and we have can process this kind of real census data. So the big data in the end. So this is a data analytics what have been developed as a Bayes inference network. And then here are the practical tools that so it can predict, can provide a prediction hourly, daily, and monthly, and based on the streaming data. So it can show whether your energy usage is abnormal or normal, so that we can send the alert directly to the facility manager. As you know that if you are working in the power management, this area facility, because we couldn't touch the energy building energy management system. So what we can do is that currently for our system, we can send the alert to the facility manager, so that facility manager can say, okay, I can turn on or turn off the heaters in which building or in which room. So this is what we have done for the City World project, and we also have a paper already published. I think this project is most fits for today's topic. But what I just want to say is that we use different data. We try to build the capability to process data. And here is the application to rail monitoring. We use data from ground penetration radar using image processing to try to detect subsurface object faults, okay? So we try to understand. Yeah, other use cases, we try to understand, build the cloud-based big data analytics for understand customer insight. This is related to manufacturing. We scrap the information from a website to perform the sentiment analysis on the customer reviews, to understand how the customer thinking about product services. Yes, and also the using parallel approach to processing the CT level data, transportation data, to make this, to understand, to help the planning support. So this is very nice use case study to demonstrate how we actually, the power of data. So how we actually use the big data to really tackle the societal challenges. Yeah, this is the, so yeah, other application, we also have applied big data into the cybersecurity. So yeah, I think I'm not going to talk too much. I really appreciate all these funders to support our research. Yeah, I think so now, yeah, I'm finished my my talk, and any questions, please do ask. Yeah, thank you very much. I hope you enjoy the talk.
Thank you very much, Professor Han, for showing us all the variety of topics that data mining can be used for, starting from medicine to agriculture to smart cities. Does anyone have any burning question? As we are slightly running behind the schedule, but hopefully we'll pick it up. Any questions for Professor Han? If you're shy, you can also use the chat box, and then we can read those questions later on.
I have one question myself, if that's okay. Okay, so thank you for the talk, very interesting one. As Jelena said, quite a range of different areas. I just wanted to know about the project with the smart cities and the energy consumption, if there is any plan regarding open data. Because as you know, power system engineers, we struggle, and for us, and doing demand-side response, any kind of open data information about the buildings is important. So I was wondering, are these data open, or are they tailored to a specific building and customer, and you are not allowed to reveal the data?
I think the city web, the overall data, they already put the like archival in the as open data, I think. But in terms of occupancy level, I don't think so, because occupancy level is that at that moment during the project period, only the academic building in the Manchester Met University, only one building. So I don't think occupancy data is available. Yeah.
Okay. I can email you then about the link for the other one. Thank you very much.
Yeah, no problem.
Thank you. Okay, we'll move on to our next speaker for the day, and then we can read through the questions at the end. We'll have time. Our next speaker is Dr. I hope I will pronounce this correctly, Arjumand Younus, who is currently working as a research scientist at a large multinational business analytics company called Affinit. Prior to that, she was a postdoctoral researcher at Consus in University College Dublin for a massive government-funded project on data-driven agriculture for Ireland. She is the co-founder of the Dublin chapter of Women in Machine Learning and Data Science, and is also actively involved with the Python Ireland community. Arjumand, welcome.
Thank you, Elena, for the very nice introduction. So I have just 10 minutes, I guess, so I'll be a little quick. If any questions you can ask towards the end. So the topic is quite related to Professor Han's talk, but I'll go a little bit more in some of the aspects of precision agriculture, which was my previous project. And I've just joined industry. I started this Monday, basically, and as a research scientist. So my talk is about big data solutions for real world problems, data science for social good, which has been my theme for about 2 or 3 years now. So first, I'll give a little bit of introduction into data as a new oil, some social challenges, what's the link between data and social challenges, and then the example from data-driven agriculture, which was my previous postdoc work. So we all know that data is very valuable. In fact, a lot of countries in the developed world, and even we, consider it as a new oil. Previously, the countries that were oil rich are now understanding that eventually their oil is going to deplete, so they need new ways of making money, and data is one of those ways. The knowledge economies and the whole term data-driven economies, it has emerged from all this abundance of data. Where is the data coming from? We have social networks, we have sensors, we have mobile data, we have lots and lots of sources of data now. And as someone also asked in the chat, is too much data also a problem? Yes, definitely it's a problem, because when you have too much data, you also have too much noise. And to get knowledge from that data is what we data scientists do, and it's not always that easy. So let's look at some social challenges of today, and they are very big challenges in line with UN's Sustainable Development Goals. They call it SDG. So we have climate change, we have food shortage, health and well-being. We want to develop secure societies. We want to finish the problem of racism, anti-immigrant sentiment. We want healthy societies. We want equality and equity for all. So how is there a link between data and social challenges? Of course, it's not obvious, but when we have data, we can do research. We can come up with research questions to using the data. And once we have the solution to research questions, we can inform policymakers that, look, the data suggests that this is a major problem. That's one way in which we can help solve them. And the second way is that we can get some insights from the data, like Professor Han showed some Alzheimer's disease detection algorithms. Like if you have algorithms that can automate all that process, we don't need so many healthcare workers, because there's a limit to how much healthcare workers can do diagnosis. So if automated algorithms can do all of that stuff, we can be quick in solving a lot of society's problems. So now, what's the biggest tool that links the data and the social challenges is the machine learning. It's basically a subfield of data science. And because we have lots of data, we now learn from that data to generate patterns, and those patterns then help us make inferences in different domains. This is a quote I really liked, that machine learning appears magical only because underlying data has a story to tell. Models simply use math to decode the story and understand the patterns. They then retell alternate versions of the story based on plot twists and what if scenarios. So as you can see, the most important thing in all of machine learning is the data, which is telling the story. And that story is what we human beings are interested in and in mining. So now I'll jump to the example of data-driven agriculture, that the project that I worked on for the past 2 years at University College Dublin. We worked in collaboration with a huge company who is operating in 7 countries in the domain of precision agriculture, and they provide their software to farmers, and the farmers have to fill out the different data fields, like they have to tell the yield, and their machines are able to get yield maps. They have weather data from weather stations, soil properties. Then they also do soil tests from sensors. One of the important data that I worked on was the electrical conductivity data, and we got this from sensors. Basically, it's from electromagnetic induction devices. I'll move on and explain. So the question that I was solving was, the research question was, how when we can use all of this data to make predictions about crop yield, whether or not we're going to have a good year next time, or maybe in 2023 or 2024. Can we predict this beforehand? Because the world is facing a food crisis, a food shortage crisis. Can we be able to solve it using machine learning? Can we optimize our food production systems? That's a major question, and it's one of the UN Sustainable Development Goals, and we need to solve this problem as quickly as possible. So one of the model that I proposed was a fancy graph-based model. It's not something new, but its application to agricultural domain is new. So first, let me tell a little bit about electromagnetic induction and soil conductivity data. Soil conductivity data is basically, you have a sensor and you detect the electrical current that can pass through the soil from one, you put it in one part and you capture it in another. So it's a geophysical method, and it helps you study how much spatial variability there is in a soil's physical, chemical, and hydrological properties. Because within, farmers have lots of fields. One farm is composed of multiple fields, and even within a field, there are different patches. Some soil patches are good, some soil patches are not so good. If you see yield maps, a thing called, you can Google it and you will see yield maps. Some areas of the fields have very high yields and they're giving very good crops, but some are, every year it's the low yield. So what is it that's causing this low yield is what we were trying to study. So I proposed a prediction method based on deep walk algorithm. As we know, deep learning is everywhere. And deep walk is basically a representation learning method for networks. Now, network science and social network analysis in this field has been around for a long time. And any problem that you can model as a network, you can use these intelligent graph network neural nets for it. And that's what we did. The patches in the soil, or you can say the yield maps were converted to a network, and then deep walk was applied to them to predict the yield at each point. So in network representation learning, basically you model your data in form of nodes and edges, and then a vector is learned. The output is a vector. This vector encapsulates, because it's called representation learning, so you're learning a representation for certain things, certain features, and that vector is capturing it. If you've heard word embedding, a lot of techniques are now built over that for text classification, because the words that even I'm speaking at the moment, they are the words that will be close together, or the words that we are saying right now, like precision agriculture, smart city, they will be in a same space because they have the same applications, or they are arising from the same applications. So this was something that came from text mining, and then I tried to apply, because my PhD was in this topic, so I tried to apply those ideas to this agricultural data, and it worked pretty well. So the problem was that we have yield points, but in a patch, in a grid of a field, the yield points are more, and we have less EC, electrical conductivity points. So first we needed a one-to-one mapping to finish this non-uniformity, because the prediction would need a one-to-one correspondence. So what I did was, we find the one that is closest to a yield point and use it as a copy, and when there's a tie, when an electrical conductivity point is near a yield point that's 2 or more yield points, we take the average of those points. So then we get a one-to-one mapping, and using this one-to-one mapping, network is constructed. Now these yellow nodes or these blue nodes, each of these blue nodes is a EC point, and it's taken as a node. So a similarity function is devised, and you consider if the similarity is above a certain threshold, I consider that to be a same node. Let's take a look at an example. So these are two grids placed alternate to each other. Now A, B, C, D, E, and F are in this one grid. Now the grid next to it, we see that A, E, and C are being repeated because of the similarity being repeated. So we consider this as one node, and then the edges and all of this are represented and given to the deep walk algorithm in this form, after which it outputs a vector for each node, and this vector is then fed into another machine learning algorithm, which can be anything, or even you can use another neural net, and the accuracy is quite improved. Earlier it was like 60% without these deep walk features, but deep walk when applied to this kind of model gave a very good result. So that was some of my work in this domain, and right now I've just recently changed role. If you have any questions or want to share anything or want to reach me out for any project or anything, I'm available on Twitter with this handle. So thank you very much.
Thank you very much, Arjumand. Would anyone like to ask any question to Arjumand before we continue? Okay, I can ask one. As someone who is on the power and energy side of the story, what is it, maybe this is a silly question, but what is it that makes deep learning so ubiquitous? It's everywhere, and it seems that all the other data mining methods have been put in the shadow. It seems that most of the methods that were used before are now maybe not needed. Are we now solving everything with deep learning?
That's true. That's true. And even there are some funny jokes, funny memes around it, that some people are using it, you know, like killing a mosquito with a hammer, and it's analogous to that. I agree somewhat, because people are even using deep learning where it's not needed, where there's a very less training data. So the two things that sparked this deep learning revolution, once again, it was there previously as well in papers of 90s, but first was the abundance of data. So now deep learning works well when we have lots of data. The traditional machine learning algorithms do not work so well. They either overfit your data or underfit your data, but deep learning has this tendency, because it's a network of connected neurons and neural nets, so it fits your data really well and gives very good outcomes. The other thing is computational power. Now we have GPUs. Earlier, we did not have that good efficiency. Computational efficiency was a huge problem, which is why a lot of researchers, even now, some research groups don't have access to GPUs and they cannot go for deep learning. This was a problem in my research group too, which we then solved. Some research groups came together and they funded a GPU and all. But now that we have these powerful machines and GPUs in research groups, so that's why a lot of deep learning is being revived for different problems, and it's giving very good results. That's my take on it.
Okay, thank you very much. That was useful. Thank you. Let's now move on to our next speaker. Dr. Ting Wu is currently a postdoc research associate at Allianz Manchester Business School, the University of Manchester. She completed her PhD in business and management in 2021, so this year. Previously, she worked as an assistant associate professor in Shanghai Liangxiu University. After she obtained her first PhD degree in engineering. Dr. Wu, the floor is yours. If you could just unmute your microphone.
Yeah.
Yes.
Thanks, Jelena. And good afternoon, everyone. Thanks to the organizer for inviting me to give a presentation in WIE event. Today, I will give a short presentation about my PhD. Sorry, I share my screen first. Yeah. So today I will give a short presentation about my PhD research in power network, which is mainly concerned with a decision support framework for the assessment of decentralized energy systems. At first, I will give a brief introduction of research background and motivation, then talk about research methodology. It's mainly concerned data envelope analysis model for energy efficiency and a hierarchical framework using the evidential reasoning approach for the assessment of decentralized energy systems, and applied this model to 2 case studies in China. Finally, I will talk about the research contribution and the future research work. The energy trilemma represents the biggest challenge currently facing the world. It includes 3 integrated issues: security, affordability, and sustainability. These 3 issues cannot be thought of independently. In order to solve the energy trilemma, renewable and decentralized energy can help us address it. Yesterday, we used traditional energy such as fossil and coal generated by big power plant, by transmission networks such as a national grid, then to the distribution network. At last arrived the consumer. Long distance, power lost, resource is not sustainable and has serious impact on environment. Renewable and decentralized energy system can move away from total reliance on central energy source and grid and enable low carbon generation in densely populated area. And the decentralized or distributed energy is usually produced close to where it is consumed. Obviously, different sources of renewable energy can be deployed at a range of different scales, from household and building to local community level, in a company with demand-side measures for reducing or shifting energy consumption. It can combine technologies to form a microgrid. And the microgrid are multi-vector, locally controlled, independent energy system. It integrates generation, storage, demand-side response, system control, and etc. So it can address the issue of security, affordability, and sustainability. And let me look at the development of decentralized energy in the UK. Figure 1 just shows the annual installed capacity of renewable energy in the UK. Figure 2 is annual renewable energy generation. Figure 3 shows the installed capacity of wind energy across the EU in 2019, with the UK have the most. And the figure 4 shows the installed capacity of wind energy in different countries of EU from 2010 to 2020. The United Kingdom was the country with the highest installed capacity in 2017, 2018, and 2019, with some decline in 2020. And this is the development, the generation capacity by type and portion of decentralized energy in UK from 2016 to 2050. We have continued to use 2x2 matrix with the axis prosperity and green ambition. So from the background introduction of these systems, especially the microgrid, as the development is a complicated research problem. There are many challenges on the development of these systems for real-world deployment. Relevant policy, legislation, and mechanism are not sufficient comprehensive, since the deployment of these systems involves a variety of aspects, such as economic incentives, energy trading management, environment protection, and demand-side management. So it is very important to evaluate the performance and the impact of these systems in terms of energy planning, environmental impact assessment, project selection, and allocation. So it is an MCDA problem, multi-criteria decision analysis problem. So the research objective just model and assess the performance, cost effectiveness, social and environmental impact of alternative these systems systematically to support informed decision making. In order to assess the energy efficiency comprehensively, we consider the achievability of energy saving and emission reduction. So we choose not only the economic input, but also separate the total energy consumption as renewable energy consumption and non-renewable energy consumption. And choose not only the desired output, GDP, but also the undesirable output, CO2 emission. And I applied 8 types basic DA models to analyze the energy efficiency in 39 countries whose GDP are the top 40 in the world. Hong Kong is not counted. The result shows the developed countries have a better performance than the developing countries. The DA models include CCR prime model, BCC prime model, and the input-oriented dual CCR and BCC model, output-oriented dual CCR and BCC model. So this is the result of energy efficiency in 2018 using BCC input-oriented prime model and BCC output-oriented dual model. In total factor energy efficiency, this result is shown in this table. We can say there are 9 countries, the efficiency score is 1, is efficient, and other countries not efficient. And the last 3 countries are Indonesia, India, and China. But if we just consider particular factor, not the total factor, we can find the energy efficiency have changed a little. We find the last 3 inefficient countries have been India, Russia, and China. China has already that increase of the efficiency is 0.5, because in recent years China has already developed more renewable energies and reduce the CO2 emission. So they increase the energy efficiency. For example, the solar energy wind farm and so on. So we can see the comparison between the 3 countries with the worst performance and the average efficiency, and in total factor and particular factor. Because the DA model can only deal with quantitative criteria, and it cannot process the quantitative, even uncertain data. So we construct a hierarchical model to deal with the performance assessment of these systems. This is the hierarchical assessment framework for the evaluation of performance multi-vector decentralized energy systems, which include technical, economic, social, and environmental aspects. For technical, it includes maturity, safety, reliability, and self-sufficiency. Economic, investment, O&M cost, payback period, service life, and construction time. Social includes social acceptability, social benefit, and the environmental, CO2 emission, land use, noise, and others. The performance assessment is a multi-criterion decision problem. There are many MCDA methods such as HP, TOPSIS, electric, fuzzy set, and so on. However, there is a lack of details about the definition, assessment grades, and the relationship among all the criteria in the existing MCDA methods. Therefore, we proposed the ER approach, evidence reasoning, to deal with the performance assessment of decentralized energy systems. The evidence reasoning is based on belief distribution. In ER MCDA, a criterion is termed as framework of discriminant and defined by H. And the belief distribution SA on H. A represents alternative, H represents the criteria defined by SA. H1, beta 1, H2, beta 2 to Hn, beta n, with beta n defined as belief degree. For example, H on mature include immature, poorly mature, mature, sufficient mature. The belief distribution SA2, it means the alternative 2 on this criteria. They have a different distribution. This is the structure about the and the graphic interpretation of evidential reasoning. So it includes the top criteria and the sub-criteria. So under the unified belief structure, both quantitative and qualitative criteria can be formulated to a belief decision matrix for further aggregation and analysis. And this method can aggregate both qualitative and quantitative information, as well as dealing with various types of uncertainty, including ignorance and randomness. In addition, the weights and the reliabilities of assessment information collected from multiple sources can also be taken into account in the generalized ER rule. On the other hand, a software package, the intelligent decision system, is also proposed by my supervisor and I, is applied to the ER method. The result of the software include not only the ranking order of the alternatives based on average scores, but also aggregated performance distribution of each alternatives and some sensitivity analysis, which would be great help in decision making. So there are two case study in China. One is a multi-vector generation microgrid system in Wuxi Industrial Park, which includes solar energy, wind energy storage, and diesel backup generation. And the other one is a microgrid cluster in the city of Inner Mongolia in China. This is an integrated D system, includes PV, wind farm, and solar thermal and energy storage facilities. The capacity is 2.5 million kilowatt in total. So this is the models in ideas for the case study one, the assessment model. So there are 4 alternatives, and the left hand is the framework. Overall performance includes technical, economic, social, and environmental aspects and sub-criteria. This is the data from each criteria and in each alternatives. This is a result of the ranking. We can say the alternative 4 have the highest score, and we can also find the distribution of each alternatives in different aspects, technical, different criteria, economic, social, and environmental. And this is the other case study. We can find the city A have got the highest score. And the sensitivity analysis and the trade-off analysis is also can be done in intelligent decision system using based on the evidence reasoning approach. Okay, this is about the research contribution. Development of DA models to analyze the energy efficiency and the environmental impact in consideration of desirable output and undesirable output. And we separate the input, the energy consumption as non-renewable consumption and renewable energy consumption. Proposed a performance assessment model of DE system from technical, economic, environmental, and social aspects, including the definition, description, and assessment grades of each criterion in the framework. Multiple criterion decision analysis. Many stakeholders, including policymakers, energy supplier, and consumers, energy networks owners, and the investors and stakeholders in local communities can apply this model to help them to make some decision and support the informative decision. And the future network is investigate the further whether the energy efficiency is affected by other factors such as policy making or environmental aspects. It would be useful to integrate to the DA result, MCD result, to conduct performance planning and the improvement holistically and comprehensively. How to construct the appropriate assessment model for general D systems with suitable criteria and the determination of assessment grade utilities in each criteria, different weight production. The conditions of using the ER approach should be validated rigorously in the research context. And some other performance assessment model for post-project assessment. Okay, this is just my presentation. Thank you for listening. Any questions?
Thank you very much, Ting. Any questions for Ting and on her multi-criteria approach? I would like to invite our next speaker, our keynote speaker, or second keynote speaker of the day, Dr. Tabia Ahmad, who received her BTech degree in electrical engineering and the MTech degree in instrumentation and control engineering in India. She has recently submitted her PhD thesis at the Indian Institute of Technology, Delhi, New Delhi, India. Presently, she's working as a postdoctoral researcher at the IEEE department of University of Strathclyde in Glasgow, working on addressing the complexity of future power systems dynamic behavior. Her research interests include power system dynamics, WAMS-based analytics, and signal processing techniques in power systems. Tabia, the floor is yours.
Thank you. Hello, everyone. I am Tabia Ahmad. Hello, everyone. I am Tabia Ahmad. I'm a research associate at the University of Strathclyde, and today I'm going to talk about advanced computational techniques for robust power system analytics. This talk has been organized by under the aegis of IEEE Women in Engineering Society Women Power UK and Ireland chapter. Before I begin, I would like to give a brief overview of what the talk actually consists of. So first and foremost, I would like to discuss the genesis of power grid, the present and future, the scope of data science and power grids, advanced system analytics, measurement data quality, equipment health diagnostics, robust state estimation, robust mode metering, power system grid frequency statistics, and detecting power grid cascading failures. The traditional power grid is basically divided into 4 sections, which consist of, at the lowermost level, we have the generating station, which traditionally produce power using fossil fuels. Then we have the generating step-up transformer, which transmits power to the transmission system. The transmission system transmits large chunks of power over long distances, so this has to be at a high transmission voltage. Then we have the step-down transformers before the distribution systems, because the distribution level voltages are what we receive at our homes. Then we have the distribution system, which supplies power to our homes, the primary customers, and finally the wall outlets of our homes. Today's power grid, along the developments in smart grid, today's power grid is moving into a data-intensive era, and the different sections of the power grid have in fact been revolutionized with an increasing innovation in terms of data science, in terms of both the generation, transmission, distribution, and so on. The generation side has been revolutionized with the addition of changing energy mix due to solar, wind, and so on, in addition to the already existing nuclear power plants, hydroelectric, and fossil fuels. The transmission and distribution system has also been revolutionized with the influx of huge amount of data. The already existing SCADA, which monitors monitors the power grid at several locations, has in fact been more or less penetrated by an increased proliferation of different grid sensors like pressure measurement units and so on. The commercial and the industrial section of the power grid has also seen huge developments in terms of electric vehicles, energy storage, smart buildings, distributed energy management systems, and things like that. As other speakers have mentioned, data science is in fact an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from data, any kind of data which could be structured, unstructured, and so on, and apply this knowledge into actionable information. Data science is actually an umbrella term comprising of data mining, machine learning, and big data. Many of the pattern recognition techniques which have been used could be applied. This could be regression techniques, dimensionality reductions like principal component analysis, clusterings, be it k-means, k-medoids, or altogether, this could also enable modeling power system problems into different graph theoretic or game theoretic frameworks. And additionally, machine learning and deep learning frameworks could also be utilized. Now, this particular slide highlights the opportunities for data science and power system. As you can see, data is the center of all different agents in power system. These could be the transmission system operator, the TSO, the distribution system operator, or these could be the end users, which are so commonly known to us in the smart grid scenario as prosumers. These could be different other stakeholders like the market operators, aggregators, and so on. These different segments may benefit from increased proliferation of data-centric applications. For example, the transmission system has already seen newer applications and improved capabilities in terms of wide area control, state estimation, real-time congestion monitoring, and so on. While the distribution system has also been or is in the path of revamping through different other novel applications like equipment, health diagnostics, asset management, and things like that. So the opportunities in data science and power system have further been revolutionized through the deployment of various sensors across power grids. These could be the phasor measurement units, which is in fact a sensor which has been regularly being deployed across different key buses of the power system to monitor different parameters or of the power grid, like the voltage, the frequency, and things that at a very high rate than the currently existing SCADA techniques. Different other devices like point-on-wave devices, digital fault recorders, smart meters offer whole new opportunities for data science. However, before applying data-centric techniques to power systems, the measurement data quality is an important concern when using data science for power system applications. And hence, the following slides would depict different applications which in fact discuss the role of measurement data quality on different power system analytics. Now, the electric power system is witnessing a significant transformation towards an active, integrated, and ubiquitously sensed fiber physical system. An abundance of multi-scale data from different devices has enabled a host of new techniques for monitoring the state of the grid. In this slide, let us consider the power system as an input-output system. The input to the power system is supposed to consist of perturbations from stochastic load and renewable energy injection. However, the output to the power grid is available to us as monitored by different sensors deployed in field. However, the quality of measurement data is corrupted by process noise and measurement noise as available in literature. Also, it has been found that the sampling statistics of noise represent non-Gaussianity from the usually, which is quite different from the usually assumed Gaussian distribution for the statistical distribution of different power system variables. Thus, this proves that either the observation or the process noise are separately or jointly non-Gaussian. The sources of noise in different measurement data could be either due to the measurement and instrumentation channel, which is preceding to any kind of sensor. This could be due to the time synchronization of the GPS clock. It could be due to the phasor estimation algorithm. However, considering other things accurate, we are going to concentrate on the measurement and instrumentation channel, which is supposed to be the primary contributor of measurement noise in data. The noise which we are going to consider here is categorized as random noise and systematic noise. Now, in order to statistically characterize the behavior of this kind of noise, it has to be extracted from field measurement data. Now, in order to extract this noise from the data, what we do is that first we take measurement data from different power systems and then filter it using a median absolute deviation based filtering scheme. And the residual, which is obtained, is in fact considered as a proxy term for noise. Now, this noise is now investigated for different statistical indexes like the probability density function, the power spectral density, and so on. Now, on further analyzing these indices, it is found that the noise extracted is in fact non-Gaussian and maybe even colored, and hence the white sense stationarity assumption of noise is violated even under ambient conditions. It is also found in this research that progressive addition of systematic error to measurement data in fact shifts its CDF, which is the mathematical dual of the probability density function, signifying that yes, indeed, the density function is biased as well as non-Gaussian. This particular slide just enumerates the steps undertaken to extract the error. These could also be found in the publication. Now, the data which is found in field or these observations have in fact been also validated under laboratory settings where data from a laboratory scale PMU has been obtained using a digital real-time simulator, and the phasors obtained are stored in a software PDC where they are analyzed further for their statistical behavior. In order to reveal the impact of the different sources of error in measurement data, we conducted a novel Gaussian mixture model-based clustering of the errors so as to reveal the source of corruption in measurement data. So after carrying out this Gaussian mixture model-based clustering approach, we indeed find that the noise clusters are biased from zero mean, and they in fact change their components as the parameters of the preceding instrumentation chain are varied. This in fact also signifies that this research could in fact be used for health monitoring and equipment diagnostics in general, and in this case, the measurement and instrumentation chain. The posterior probability, which is the probability of each component of the Gaussian mixture model, is in fact the estimated probability that each particular data point came from that component. This would in fact help in signifying the faulty element of the measurement and instrumentation chain, which could be probably a saturating CT or a faulty cable or burden impedances. Additional details could be found in the publication cited here. Now, I would like to discuss few future prospects of PMU data quality analytics. Presently, there's a concerted effort by various power utilities to use big data and data quality analytics for different power system applications. Utilities and vendors are developing more and more synchrophasor-based decision-making tools for higher sampling rate and accuracy compared to the traditional SCADA data. Also, the typical bad data ratio, which is found in synchrophasor data, varies from 10 to 17%. Thus, there's an urgent need to develop scalable frameworks to monitor and improve the quality of measurement data. This would also help in generation of experimental PMU data or synthetic data in close conformity with field data, bad data removal, missing data protection, and so on. Now, the second application of data science in power system is perhaps the huge domain of power system state estimation. The immeasurable states of the power system are in fact estimated using state estimation techniques, which could be broadly classified into dynamic and static based on the time scale which we are interested in. So now the question arises, why robust dynamic state estimations? We have seen huge number of techniques available in literature which use dynamic state estimation based on Kalman derivatives to estimate the value of immeasurable states and dynamic states in power systems like the rotor speed and things like that, the angle, the machine angle and things like that. However, when the field measurement data, which is found in field, is corrupted with large measurement bias, non-Gaussian noise, lossy data, measurement delays, and things like that, how to conduct robust state estimation. This research focuses on manipulating or rather dealing with process noise covariance and observation noise covariance matrix, which are inherently non-Gaussian given the corrupted data, and then These techniques are incorporated into an information-centric filter, which is based on the chorentropy technique to give a particular accurate estimation of state under these conditions. This particular test case consists of measurement data, which is corrupted with non-Gaussian and colored noise. And as we can see from the figure here, that the proposed chorentropy-based uncentered information filter accurately tracks the true state, while the other state-of-the-art techniques do not in the presence of non-Gaussian outliers. The second technique where data-centric technique to maybe assess the situational awareness of the power grid is in fact the power system mode metering architecture. Since earlier times, this mode metering has been always used to detect troublesome modes in power system, which are oscillations encountered in power system. Although different types of physics-informed techniques have already been used, measurement data-based techniques are also used to detect modes in power system. However, with increasing uncertainty in power system measurement data, modal oscillation techniques based on measurement data may be corrupted and might give incorrect results, which could be detrimental to power system security. So the present work here develops a generalized correlation-based mode metering approach due to the non-Gaussian nature of measurement noise and impulsive outliers. The widespread stationarity assumption of power system measurements is violated even under ambient conditions. Under such a scenario, we cannot expect mean square based, cost function based techniques to perform good in the presence of such kinds of outliers, and hence the proposed research takes care of these anomalies by proposing a generalized correlation cost function for mode metering architecture. This includes a test case study where the mode metering results for 19 machine test systems using the traditionally used MEC-based cost function and generalized correlation-based mode metering architecture. As you can see, the figure A consists of some spurious modes and modes which are not properly detected, or in fact, these could even be just noise and not accurate mode. However, the present techniques leads to a fair detection of modes under these conditions. Thus, it is found that field power system data, when manifested with heavy-tailed non-Gaussian noise, if utilized for calculating metrics of situational awareness, may be detrimental to power system security. Towards this end, this work proposes robust formulations for DSE and mode metering, along with possible considerations for their real-time implementation. Now, the next application of data science in power system is perhaps monitoring the steady state or the quasi-steady state statistical distribution of key power system parameters like the power system frequency in stochastic power system. It has been asserted that the statistical distribution of frequency across various power systems across the globe shows a non-Gaussian statistical distribution, which could have wide-ranging impacts and, in fact, give an overview of the wide range of deterministic and stochastic input processes which could be affecting such a probability distribution function. Here depicted are the probability density function, or the PDF of frequency, which is observed in frequency measurement data captured from open access data sets from UK, India, and France. It is quite clear that the PDF of frequency is non-Gaussian and bimodal, while it is also skewed. The kurtosis, which is the fourth order moment of which is basically used to reveal the non-Gaussianity, also shows a consistently higher value than 3, thus signifying that the data is significantly non-Gaussian across different time scales too. Another index to offer an insight into the nature of these time series data of frequency measurements is the autocorrelation function. The autocorrelation function for these frequency data sets which are captured in field shows that initially the autocorrelation shows an exponential decline followed by a steady state value with several oscillations. This also shows that initially the power system is subjected to the inertial response or the response due to the internal power system behavior, and finally over larger time scales the statistics is in fact a depiction of the input processes into play, which could be the renewable energy injections or stochastic loads. Thus, the statistical characterization of power system frequency increment through its PDF and autocorrelation function reveals its non-Gaussian character and heavy tails. This anomalous diffusive behavior of power system frequency also exhibits a multi-scale property, which could be further utilized for designing different control schemes, demand and management schemes, or rather an altogether new modeling framework for these different parameters. These results have also been verified under simulation settings apart from the field data, and we obtained quite similar results of non-Gaussian distributions. Now, another part of this work also investigates how the statistics of input, that is, for example, if we have a power system in hand, and if the statistics of the input, or which are the renewable energy injections and loads at any node, how they are affected, or the output statistics are affected from the input. This work has been done in, although it is data driven in the sense that the statistics are derived from the statistics of data which is found in field. There's a lot of physics informed, so the name physics informed data driven technique. Finally, I would like to discuss another pressing application in power system these days, which is cascading failures in power system. There are several notable blackouts have happened in the past, which have been catastrophic in nature. This could be the historic blackouts, or the most recent Texas rotating blackouts, or the UK blackout of August 9. Then there was a massive blackout in northern India, which affected around 30 to 31 million people. Now, apart from the size of the blackouts in megawatts, the social costs of blackouts are also huge, thereby prompting us to maybe study these cascading failures, their evolution, so that they could be not averted, but significant control action taken within time. So due to the huge combinatorial nature of the problem and the number of power system components involved, we are investigating this problem in the light of deep learning. So there have been different studies involving deep learning or machine learning in general to study cascading failures based on recurrent neural networks, or these could be SVM based, but currently our approach is based on graph neural networks, because we believe that apart from the deep learning formulation of the problem, there has to be some kind of physics which has to be included in the system to make the technique more reliable, because there have been several studies indicating the statistical inaccuracy or the reliability or theoretical guarantees for deep learning. Now, the nature of the problem is such that the data is spatiotemporal in nature. It has also been found that the failures show non-localized behavior, in the sense that if a component fails, it is not necessary that the component which is nearby to the affected component fails. The failures could propagate way long across different regions. So basically, the problem is a large-scale classification problem, which is combinatorial in nature. And we find that graph convolutional networks could be better suited to study this large problem, which also include an aspect of topology, or the graph Laplacian, which offers a physics-informed nature to this. Now, after discussing these possible applications of data science and power and energy, I would like to stress on the future goals, or rather what is expected in this field. The ultimate goal of harnessing big data in power systems is to maintain the security of the grid, improve customer service, and achieve business goals while increasing the reliability, resiliency, and efficiency of operations. So this is in fact needs an open architecture which is based on standards, so as the techniques which have been proposed could be utilized by industry and academia in order to develop integrated frameworks. So standards is the need of the hour. Also, we should also consider the keeping in mind that the power system is evolving as a huge cyber physical system. Cybersecurity risks are also there, so we need to take that into account. Also, apart from these challenges, I would also like to stress upon the statistical confidence which needs to be established in these data-centric techniques, apart from or just applying deep learning or data-centric techniques to to the power grid operations, their statistical confidence and theoretical guarantees need to be established because power system is in fact a critical infrastructure. So this was all from my side. Thank you.
Thank you very much, Tabia, for this keynote. Would anyone like to ask any questions? Now that we have moved to the power and energy side of data science. Actually, my question was your last slide that I wanted to ask about your view on what are the aspects of the modern grids that require data science, but you have answered my questions. I would only add the complex systems to this list, because now we have multi-energy systems, the IT systems, which are in a way combined with the power system. So there's a lot of research looking into this, and I believe that data science is also very much required in this area. Maybe there are people in the audience who are dealing with this topic as well. Would anyone like to ask any questions? Any comments?
I think yes, from my side, I would agree on that because I also checked that there was a question before in the audience, and I think yes, so data science seems to be quite needed, but I guess from a lot of us being power system engineers, we have this this question if it is a mix between needed and popularity. You know, in a sense, everyone is using data science, so I have to use it as well. Because, for example, I am quite involved in electricity price forecasting. And if I would try to use my models for 2040, I definitely know that data science couldn't really help me. So I would really need to stick to the traditional power system like unit commitment models. So I think maybe in the end it is a combination. So we have to accept that some areas they will stay in the traditional models, that they still being improved, and some others they will probably move to data science. That's my personal view, at least from the price forecasting area. All right.
Yeah, exactly. I think it should be a mix, or rather, if we are resorting to these kinds of techniques, they should be backed up by theory, in fact, so that their mal-operation could be detected beforehand.
Good, thank you.
And also what Tabia mentioned, the probabilistic modeling is very important now with all the uncertainties coming from all the different sources from which some we didn't have before. Any other questions or comments?
If I may just make a very quick comment just along the line of the comments that were made before. Actually, I fully agree that a combination of, let's say, more analytical traditional methods and machine learning or data-driven methods might be very interesting to explore, because, for example, machine learning techniques might suffer from having not much robustness to small perturbation. For example, this is a general drawback of these types of techniques. And also when it comes to decision making, they're very powerful when we have to make complex decisions or decide about complex control tasks, because I come more from the control area. But on the other hand, they cannot guarantee the satisfaction of constraints, for example. So there is an area of research now about combining, for example, more analytical predictive based decision making and machine learning that might be promising to explore. This is just a comment I wanted to make.
Thank you, Alessandra. Thanks a lot. Any other questions, or should we continue? Okay, let's continue now to our next speaker, Ms Ana Radovanovic, who received her bachelor and master degrees in electrical engineering and computer science from the University of Belgrade in Serbia. She's currently working towards a PhD degree at the Department of Electrical and Electronic Engineering at the University of Manchester in the areas of renewable energy sources and power system dynamics. Anna, the floor is yours.
Thank you, Jelena. Hello, everyone. Thank you, Jelena, for the introduction and for inviting me to be part of this event. So I'll start sharing my screen now. Okay, so can you see my screen?
Yeah.
Okay, thanks. So I'll give a brief talk on the application of clustering algorithms in the analysis of the impact of hybrid renewable energy source plants on power system stability. So first, just I will introduce you to the concept of hybrid renewable energy source plants. So as Tabia has already mentioned, over the past several years, there has been significant increase in the installation capacity of renewable energy sources, and this has resulted in many changes in power system structure and operation. One of the main drawbacks of renewables is that their intermittent, uncontrollable power production due to dependency on weather conditions. And in order to solve these issues, hybrid renewable energy source plants have been proposed. So these plants represent the combination of several renewable generation and storage technologies. And the whole concept relies on the ability of different sources to compensate each other deficiencies to a certain extent. So the idea is to obtain, by combining different technologies, to obtain a stable and controllable power output from renewables. So in this way, we can have a controllable power production, just as in the case of conventional synchronous machine-based power plants. So far, the focus of the research on hybrid power plants has been mostly on economic and environmental benefits of their integration into power systems. Much less attention has been paid to their contribution to the overall power system stability and dynamic performance. Now, with a constant decrease in the installation capacity of renewable energy sources, and also due to the trend of decommissioning of conventional synchronous machines, it is becoming necessary to take into account their impact on the overall power system stability when deciding on hybrid plant operating point for a certain time period. So analyzing the influence of hybrid power plants on power system stability requires their adequate representation in system stability studies. So now there are two options for representing these plants in system stability simulations. One option is to use the detailed full-scale model of the hybrid power plant, that is to model each individual technology in detail. But this is not very practical, as detailed models are usually high-order models, and they often require data about renewable energy sources and their control systems, which are not available to system operators. In addition, detailed plant model or detailed model of any network cannot be exchanged between different network operators due to confidentiality reasons. So these are the reasons why equivalent models of hybrid power plants have been recommended for their representation in system stability simulations. Now, the research on equivalent modeling of single technology-based power plant has been well established. But when it comes to the research on equivalent modeling of hybrid renewable energy source plants, that research is still at early stages. So the main problem is how to select, how to define the adequate equivalent model structure, given that hybrid power plants contain several renewable generation or storage technologies, and these individual technologies can have very different static and dynamic characteristics. Also, the problem is how to develop a model that is going to be suitable for a wide range of plant operating conditions. So we don't want to develop a model that, well, actually to develop the methodology and then to have to change the equivalent model for every single hour during the day. So we just want to have like a model that we can use, for example, for the whole day or for longer time periods. And so data-driven equivalent models have been seen as a promising option to try to solve these two issues. So over the past years, there has been a significant interest in the installation of different types of measurement devices in power systems. And this has led to the availability of large measurement data sets. Now, when we have a large amount of data, we can try to use appropriate data mining methods and try to get some information about the behavior of power system in the case of different operating points and different types of disturbances. So in this research, we use the clustering algorithms for trying to establish a foundation for developing equivalent models of hybrid power plants. So clustering algorithms are unsupervised data mining methods that can identify similarities between different objects. In this research, clustering algorithms were used for two clustering tasks. The first one is the identification of typical annual plant operating points during the year. So the idea is to identify patterns in the behavior of hybrid plant operation throughout the year, and then use only these representative operating scenarios when developing equivalent models of the whole hybrid power plant. So using only representative annual plant operating points, or so-called annual plant compositions, we can eliminate the need for analyzing all possible but highly unlikely operating scenarios, and thus we can have a computationally efficient modeling procedure. The second clustering task is related to the identification of patterns in the behavior of the overall power system with the integrated hybrid power plant. So we use cluster methods to identify groups or clusters of system stability results, and then groups of hybrid plant compositions that produce system stability results that are allocated to the same cluster. It can be represented by a same equivalent model, as these operating points have similar impact on the overall power system stability. So the number of clusters of system stability results defines the number of equivalent models required for representing the whole hybrid plant in system stability simulations throughout the year. So in this study, we used this small test system. The test hybrid power plant contains 6 individual technologies, 2 non-dispatchable and 3 dispatchable renewable energy sources, along with a battery energy storage system. All these 6 individual technologies are connected to the same bus in a small transmission network. So we use one-year historical plant production data set for identifying a typical annual plant operating points. 3 types of system stability studies were performed: voltage, smooth disturbance, and transient. And we also took into account uncertainties in power output and location of individual plants in this test hybrid power plant using a probabilistic Monte Carlo approach. 3 clustering algorithms were tested: the K-matrix, the fuzzy means, and the hierarchical clustering. All these 3 clustering algorithms can be considered as representatives of 3 different types of clustering approaches. Also, 3 algorithms are widely applied. They were used for similar clustering tasks in the past, and they're also available in publicly available software packages. So the clustering of historical plant production data set resulted in only 9 typical annual plant compositions. So this represents a significant reduction in the number of operating points required for developing equivalent models of hybrid power plant, given that the historical data set contains 1-year data with a 1-hour time step. These 9 typical plant compositions resulted in different number of clusters in the 3 considered system stability simulations, even though the number of clusters is different, but it's very small for each of these type of system stability simulations. So there are 5 clusters in the case of voltage stability, 4 in the case of small disturbance, and 8 in the case of transient stability analysis. So we try to assess which clustering methods are more suitable for each of these three types of system stability simulations. And the assessment was carried out based on the quality of the obtained clustering results. So based on the compactness of the obtained clusters and the similarity between the clusters. So the fuzzy Siemens clustering method has shown to be the most suitable for static data sets, that is for the clustering of historical plant production data and for the results of voltage and small signal stability analysis. Now, even though the results of both voltage and small signal stability analysis are two-dimensional data sets, and they're also not don't contain a lot of data, different algorithms have shown to be more suitable for voltage stability, while it didn't result in very good clustering results when applied to small signal stability analysis. So the K-matrix has shown to be adequate for voltage stability, but it didn't provide high-quality clusters in the case of small signal stability analysis. And similarly, the hierarchical clustering resulted in very good clusters in the case of small signal stability, but it appeared not to be suitable for the analysis of the results of voltage stability analysis. On the other hand, the results of transit stability studies are time series data. So these results involve dynamic active power responses of the hybrid power plant to short circuit fault in the system. And in this case, only the hierarchical clustering resulted in algorithms didn't perform very well. So the type of the clustering data and the structure of the clustering data set have a very strong impact on the suitability of a certain clustering method for a particular power system stability analysis. So different number of clusters in different types of system stability simulations means that a different number of equivalent models is required for representing the whole hybrid plant in power system stability simulations. So the procedure provides the information about groups of historical plant compositions that are allocated to each of the clusters of system stability results. And these groups are shown in the form box plot in this slide. So we can develop an equivalent model for each of these groups of historical plant composition. These equivalent models can be developed offline and then stored in the library of the dedicated software package. And then the system operator can select the adequate equivalent model at any time during the year just by having the information about hybrid plant composition, which significantly simplifies the procedure of selecting the appropriate equivalent model. So I'll just briefly sum up. Our research has shown that the clustering algorithms can be used for developing equivalent models of hybrid power plants. The results obtained with the test system have shown that a few clusters, that basically few equivalent models are required for representing the whole hybrid plant in system stability simulations throughout the year. The use of equivalent instead of detailed plant models would result in more computationally efficient power system stability simulations and would also reduce the modeling effort, as if all of these equivalent models, the databases of equivalent models, can be developed only once and then used throughout the year depending on the information about the hybrid plant composition. So this would be it from my side. If you have any questions, I'll be happy to try to answer them.
Thank you very much, Ana, for your presentation. Does anyone have questions for Ana or any comments? Okay, I can ask one question about these different clustering methods. So is the aim of these methods to use these clusters in real time, or this is something that the system operator would be using offline? In other words, is there a necessity for very fast data mining procedures, or this is something that doesn't have to be done in real time, can be done?
This can be done offline, so you can do it like offline. You don't have a need to use like some fast computing clustering algorithms. But of course, once we develop equivalent models, we can then from time to time verify them, basically verify their accuracy by using like more recent historical data. And so in that sense, we can from time to time do some kind of repeat clustering, repeat the whole procedure and see whether we can adjust our equivalent models or not.
And are there any situations where this type of clustering would be needed in real time?
I don't think so, because if we want to analyze, develop equivalent models, we usually would do it like in offline, not in real time. And then we basically to have like the database ready before we start performing any types of sensitivity analysis.
Okay, thank you very much.
Thank you.
Any other questions for Anna? Okay, in that case, I will announce our final speaker of the day. Last but not least, Ms. Eleni Tsotopoulou, who received the MEng degree in electrical and computer engineering in Greece and the MSc in wind energy systems from the University of Strathclyde with distinction in Glasgow, UK. She is currently a PhD student at the Department of Electronic and Electrical Engineering at the University of Strathclyde. Her main research interests lie within the area of power system protection, automation and control of future power grids, incorporating increased penetration of renewable energy sources, integration of distributed generation, and applied superconductivity. Eleni, the floor is yours.
Yeah, I will share my screen. Okay. I think you can see my slide, right? Okay, hello everyone. My name is Eleni Tsotopoulou and I'm a PhD student at the University of Strathclyde. And today I will present you part of my research, which is about a data-driven protection scheme for superconducting-based electricity grids. This is the agenda of today's presentation. I will talk about a little bit about the scope and the objectives of my research, the background and the motivation behind the presented research, some basic principles of superconductivity, the modeling of the superconducting cable, and the proposed algorithms, and of course the results and the conclusions. Regarding the background and the motivation of this research, we have to take a look at the changes and the new challenges that the integration of superconducting cables have brought in conjunction with the converter interface sources in power systems. Generally, the deployment of multi-layer superconducting cables have been considered as a promising solution due to their unique characteristics, which contain the high current capability, low losses, and high power transfer. However, due to their unique electromagnetic characteristics, the performance of the superconducting cables must be investigated, and specifically during transient conditions. Therefore, the integration of superconducting cables with the renewable sources and inverter-connected generation have changed the physical infrastructure of the power grids and the information layer of the power grids. Today, the power systems are more subject to control than physics. So we have to take all these factors in consideration in order to design effective and reliable protection schemes, because the existing conventional relays may fail to provide secure protection and secure power systems. For that reason, there is need for a novel protection scheme which will take into consideration the variable resistance of the superconducting cables, the quenching phenomenon, and the reduced fault currents due to the inherent fault current limiting capability of the superconducting cables. As the protection of the superconducting cables has been an emerging research area due to the particularities of this technology, we proposed protection algorithms based on the combination of signal processing techniques as stationary wavelet transform and data-driven methods in order to disclose information from the transient performance of and useful information from the transient performance of the superconducting cables. The steps and the objectives of this research contain the appropriate literature review for the protection challenges. We model a simplified superconducting cable with high temperature superconducting tapes and copper stabilizer layer. And we use it for the transient simulation-based technique in order to investigate its transient performance. The development of the protection algorithms, of course, the testing of the protection algorithms, and at the end, the real-time validation of the protection algorithms. Some superconductivity. Generally, the performance of the superconductors are mainly determined from their electromagnetic characteristics, which contain the critical current, the critical temperature, and the critical magnetic field. The superconductors operate at three distinct stages. The first stage is the superconducting state, at which they present approximately zero resistance and show very low losses. Once a transient event occurs and the current, such as fault, and the current exceeds the value of the critical current, they insert to the flux flow state. And once the temperature becomes higher than the critical temperature, we have the normal state at which they present very high values of the resistance. This is the basic equation that we use for the modeling of the cable. And this is the equivalent electrical circuit of the cable. We use the pi section in order to implement the inductances and the capacitances. And as we can see, each phase consists of two copper stabilizer layers connected in parallel with an HTS layer. The resistance of the HTS layer modeled as a variable resistance in order to model the quenching phenomenon, and the resistance of the copper stabilizer layer has been considered fixed until a certain value of the temperature, and after that, it's a function of the temperature. This is the flow, give me a second, the flow chart that we use in order to do the modeling in MATLAB Simulink software of the cable. And this is the system under test in which we integrated the superconducting cable. It's a 5 kilometer, 33 kV cable. This table presents the specifications of the cable. The system under test contains a voltage source, which represents the transmission equivalent system, and two generation units, a synchronous machine and an inverter connected wind farm. At this system under test, we simulate different transient scenarios, such as internal faults on the superconducting cable, external faults on the adjacent lines, and load switching events, in order to investigate its transient performance. Figure 5 and Figure 6 shows the results. Figure 5, it's about a three-phase solid fault at 50% of the cable's length. And as we can see, during the steady state, the whole current flows through the HTS layer. Once the fault occurs at 3.06, we have high peaks of fault current, which exceed the value of the critical current, so we have the quenching, and the whole current has been diverted to the copper stabilizer layer. Another observation here is that we have reduced fault current compared to the initial fault peaks. This figure here provides a deeper insight for the impact of the fault resistance on quenching phenomenon. We have the same fault type at 50% of the cable length, but with this time with fault resistance equal to 50 ohm. As we can see here, the fault resistance, the fault current is predominantly reduced by the fault resistance. So in this case, we don't have the quenching phenomenon, and we don't have change in the current distribution, making the highly resistive faults really challenging from protection perspective. So this diagram presents our proposed algorithm. The first steps refers to the signal acquisition, at which we measure the currents and the voltages flowing through the HTS layer and the copper stabilizer layer with sampling frequency 20 kilohertz. They pass through anti-analyzing filters, normalized and packaged at appropriate windows in order to be processed to the SWT technique, which is the second stage. The SWT technique is a signal processing technique which is utilized in order to detect singularities of the initial signals. We used dB4 mother wavelet, and we went until the second decomposition level. This graph here presents the detail coefficients of level 1 and level 2 decomposition. The stage 3 refers to the future extraction, at which, based on a window-based method, we calculate the sum, the mean, the standard deviation, and the energy of the detail coefficient calculated in the previous steps for decomposition level 1 and 2. This graph here shows the peaks of the sum of detail coefficients for level 1 and 2. Now, the monitor values are normalized, and the future vectors extracted from the previous step normalized as well, in order to create a Python-based database using the PyTorch library, in order to go to the final step, which is the binary classification. For that case, we use two classifiers, one ANN and one SVM classifiers, and we use these future vectors as inputs in order to train the classifiers. Here we have a binary classification problem. So for this case, 1 indicates the detection of the internal fault and initiates the corresponding tripping signal, and 0 corresponds to the detection of another transient event, such as external fault or load switching event. As I said, we have the Python-based dataset, and we split the dataset in training set, validation set, and test set. Firstly, we select the artificial neural network as classifier because they are really common for fault analysis of the power system due to their capability to incorporate with dynamic changes and to find solutions for the nonlinear complex equations. In order to find the appropriate hyperparameters, we use the combination of grid search and k-fold cross-validation technique in order to define the final model. This is the architecture of our developed ANN. We have the input layer with the number of neurons equal to the number of the futures. We have the hidden layers at which we use the dropout technique in order to accelerate the learning process. And for the output, we have one neuron with one log sigmoid function, which is the probability for each class. In order to convert this probability to a label of a class, 0, 1, we use 0.9 decision boundary. This ANN classifier has been, has been compared with a common classifier as support vector machine. We use the same database, and again for the hyperparameter tuning, we use the grid search and cross-validation technique, and this is the final values of our SVM model. Now, we did two types of testing, an offline testing and online testing. For the offline testing, both classifiers have been tested on the 20% of the initial dataset. As a metric for the evaluation of the classifier performance, we use the accuracy. And as we can see here, the accuracy of ANN is 99.74%, and the accuracy of the SVM is 99.69%. For the online test, we use this testing environment at which the initial waveforms from the Simulink were stored for post-processing and uploaded to PCA, and after, they injected sample by sample to another PCB in order to initiate the appropriate tripping signal. This graph here shows the whole procedure for the online testing. At the first point, we have the initial signals. The second line corresponds to the detailed coefficients of the SWT technique, and the rest correspond to the peaks of the future vectors obtained with the window-based method. And here we have the tripping signal. This fault corresponds to the phase to ground fault, solid fault at 10% of the superconducting cable length. And as we can see, both classifiers can detect it and initiate the appropriate signal with ANN be faster. This slide shows the sensitivity and the stability of the protection scheme because, as we can see here, we have an external fault and a low switching event, which cause the quenching of the superconducting cable. But as we can see, both classifiers have been trained well, so they don't initiate any tripping signal for this case. And in comparison, on the other hand, we have a highly resistive internal fault, which does not cause the quenching of the superconducting cable. And in this case, both classifiers can detect it with ANN be faster again. For the online testing, we evaluate the time performance of both binary classifiers. And for that reason, we used 100 additional internal fault cases, which do not belong in the initial dataset. As we can see from this table, both classifiers can detect all the internal faults within acceptable time. Again, the ANN is faster. And in order to validate this, we run both algorithms at different PCs. This table here shows the specification of each PC. And as we can see, the developed ANN, both classifiers have acceptable time in terms of protection perspective, but ANN is faster, and it is logical because the algorithm of SVM is more complex compared to ANN, because the complexity of SVM is based on the selection of the kernel function and the number of the support vectors. When we have problems with a lot of data, probably the SVM can result in computation burden. And in that case, we have a big number of support vectors, so we have higher execution time of the SVM algorithm. So regarding my result, as we can see, as we saw, the fault resistance impacts on the transient performance of the superconducting cable and the quenching phenomenon. The developed algorithms provide fast and discriminative protection, and on the other hand, remain stable for other transient events. For the real-time implementation, both trained classifiers are capable of running correctly in real time. The ANN classifier is better for the real-time implementation as it showed higher prediction speed and initiated tripping signal in lower time scale. And regarding the sensitivity analysis on hardware requirements, we saw that for the proposed protection scheme, we don't need very expensive computers, and that highlight and the wider adoption of the proposed protection scheme. Thank you.
Thank you very much, Eleni, for your presentation. Any questions from the audience? I know it's already the end of the working day, but still. Eleni, a question from me. So are any of these data mining methods already used in practice for power system protection?
Sorry, if ANN and SVM classifier, you mean?
So yes, for example, so are data mining methods used in practice for power system protection schemes, or is this still at a research level?
No, they're widely used in power system generally, but in terms of the superconducting based cable systems, they are not so common, because as we generally until now for the superconducting cables, the combination of overcurrent or differential protection has been investigated, but due to the quenching phenomenon, there were a lot of challenges. And now the whole research has been diverted to data-driven based methods. And actually, until now, based on the literature review, there is only one paper which investigate based on machine learning techniques, series faults, but for the DC superconducting cables.
Mm-hmm. So it
appropriate, because in order to provide the appropriate protection for the superconducting cable, you have to take at the same time a lot of parameters into consideration. And that's why we thought that with machine learning techniques.
So it will also depend on the types of power lines. If thank you very much.